There's something eerily beautiful about the way the universe mirrors itself, like a cosmic hall of mirrors, where the largest structures in existence reflect the smallest wonders of our own minds. Picture this: trillions of galaxies strung together by invisible threads of dark matter, forming a web so vast it stretches across billions of light years. Now here's the astonishing part: that web doesn't just look random. It's arranged in patterns almost identical to the neural networks firing inside your brain right now. It's as if the universe has been quietly whispering a secret hidden in plain sight. The same forces that shape galaxies might also shape the way we think. Dark matter, the ghostly substance that makes up 85% of everything in existence, doesn't just sit idly in space. It's the unseen architect, the invisible hand molding the cosmos into a structure so complex, so finely tuned, that it rivals the most intricate designs nature has ever produced. And yet, despite its overwhelming presence, we can't see it, touch it, or even fully understand it. It's a mystery wrapped in an enigma, hidden in the darkness between stars. But what if I told you that by studying these shadowy threads, we're not just unlocking the secrets of the universe, we're also uncovering something profound about the very fabric of reality itself. This is where science meets the sublime. The same mathematical patterns that describe how galaxies cluster together also appear in the branching veins of a leaf, the flow of rivers, and yes, even the synapses of the human brain. It's a connection so strange, so unexpected, that it feels almost poetic. How could something as vast as the cosmic web share a blueprint with the delicate wiring inside our heads? That's the question we're going to explore today, diving deep into the latest discoveries that blur the line between astrophysics and neuroscience. By the end of this journey, you'll never look at the night sky or your own thoughts the same way again. So let's begin. The universe is waiting. Think of dark matter like the invisible ink of the universe, written everywhere, shaping everything, yet completely unseen by our eyes. We know it's there not because we can detect it directly, but because the cosmos behaves in ways that would be impossible without its hidden influence. Stars whirl around galaxies faster than they should. Galaxies themselves move in clusters as if tugged by something we can't see. Even light bends around empty patches of space, warping like a funhouse mirror. All of these cosmic quirks point to one conclusion: there's far more to the universe than meets the eye. What makes dark matter so baffling isn't just its invisibility, it's how differently it interacts with the world compared to the matter we know. Normal matter, the stuff that makes up planets, stars, and even us, clumps together, collides, and gives off energy. But dark matter, it doesn't do any of that. It doesn't shine, it doesn't bump into things, and it doesn't heat up. Instead, it flows through the cosmos like a ghost, barely noticing the ordinary matter around it. Yet, despite this aloofness, its gravitational pull is what holds galaxies together, preventing them from spinning apart into the void. Here's where things get even stranger. Without dark matter, the universe as we know it wouldn't exist. In the early cosmos, tiny ripples of density slight over clumps of dark matter acted like cosmic seeds. Ordinary matter, attracted by gravity, pooled around these invisible knots, eventually igniting into stars and galaxies. The dark matter scaffold didn't just influence where galaxies formed, it determined the very structure of the cosmic web, the grand filamentary network connecting everything. It's almost as if the universe had a hidden blueprint, and dark matter was the architect tracing the lines before the builders even arrived. So if dark matter is everywhere, why can't we grab a piece of it? The answer lies in its elusive nature. Scientists have spent decades searching for it, building detectors deep underground, scanning the skies for faint signals, even smashing particles together in hopes of creating it. So far, no luck. It's like trying to catch smoke with your bare hands. Yet, with every experiment that comes up empty, we learn a little more about what dark matter isn't, narrowing down the possibilities until, one day, we might finally unveil its true identity. Until then, this cosmic phantom remains one of the greatest puzzles in science, a silent, invisible force that built the universe, and yet refuses to reveal itself. The cosmic web isn't just a static backdrop of the universe, it's a dynamic, living structure, constantly evolving under the silent influence of dark matter. Imagine standing far enough away to see the entire cosmos in one glance. What you'd witness isn't a scattered mess of galaxies, but an elegant, interconnected tapestry, with luminous galaxies clustering like glowing jewels at the intersections of dark, thread-like filaments. These filaments, though nearly invisible, are the highways of the universe, channeling gas and matter over incomprehensible distances. And just like a spider's web trembles when a single strand is plucked, disturbances in the cosmic web ripple across space, shaping the destiny of everything within it. What's truly mind-bending is how closely this cosmic architecture resembles another intricate network, the human brain. Zoom in on a brain cell, and you'll see branches extending like tendrils, connecting to other cells in a vast, pulsating web of information. Zoom out to the universe, and galaxies cling to dark matter filaments in eerily similar patterns. Both systems thrive on connectivity, with nodes, whether neurons or galaxies, communicating through their delicate threads. The difference: one operates on gravity and dark matter, the other on electricity and chemistry. Yet the underlying blueprint feels hauntingly familiar, as if nature has a favorite design it keeps revisiting at vastly different scales. This resemblance isn't just poetic coincidence, it's a clue hidden in the mathematics. Scientists studying the cosmic web found that the distribution of galaxies follows the same statistical patterns as neurons firing in a brain. Both networks balance efficiency and resilience, optimizing connections to transmit signals, or in the universe's case, gravitational influences, as effectively as possible. It's as if the universe and the brain stumbled upon the same solution to the same problem: how to build a complex, interconnected system that doesn't collapse under its own weight. But why would two seemingly unrelated systems converge on such similar structures? One theory points to the universal laws of physics, which govern everything from the smallest particles to the largest galaxy clusters. Under the right conditions, gravity and dark matter sculpt matter into filaments, just as electrical signals and growth factors shape neural pathways. Another idea suggests it's all about energy efficiency. Both networks evolve to minimize wasted effort, whether it's a brain conserving precious resources or a galaxy cluster settling into the most stable configuration. Whatever the reason, this cosmic mirroring forces us to reconsider how deeply interconnected reality might truly be. The cosmic web also holds the key to understanding how the universe grew up. In its early days, the cosmos was a nearly uniform soup of matter and energy. But thanks to dark matter's gravitational nudges, tiny fluctuations snowballed into the vast filaments we see today. Galaxies didn't form in isolation, they were born along these invisible threads, drawn together like dew droplets on a spider's silk. Without this intricate scaffolding, stars might have scattered randomly, leaving the universe a lonely, disjointed place. Instead, we have a cosmos woven together in a web of breathtaking complexity, one that, against all odds, reflects the very networks that allow us to ponder its existence. The human brain is a universe in miniature, a 3-pound cosmos where billions of neurons fire in intricate patterns, weaving thoughts, memories, and dreams. Each neuron reaches out with delicate branches, forming synapses that crackle with electrical whispers. These connections aren't random. They're organized into a sprawling network, optimized over millions of years of evolution to process information with staggering efficiency. Now shift your gaze from the microscopic to the astronomical. Out there, in the vast darkness between galaxies, another network hums with invisible activity. Dark matter filaments stretch across the void, guiding rivers of gas and galaxies like celestial traffic lanes. The resemblance is uncanny. Two systems operating at scales billions of times apart, yet following eerily similar blueprints. What's striking isn't just the visual similarity, it's how both networks function. In the brain, neurons communicate through bursts of electricity, relaying signals that ignite ideas or store experiences. The cosmic web, meanwhile, transmits gravitational forces along its filaments, orchestrating the dance of galaxies. Both systems rely on nodes, neurons in one, galaxies in the other, connected by threads that balance strength and flexibility. Too many connections and the network becomes sluggish, too few and it fractures. Evolution and cosmology arrived at the same solution, a delicate, fractal-like balance between order and chaos. This parallel goes deeper than structure. Studies reveal that the brain's neural networks and the cosmic web share nearly identical mathematical patterns in how they distribute connections. Both exhibit what scientists call small world properties, clusters of tightly linked nodes with just enough long-range bridges to keep the system nimble. Your brain uses this design to jump from recalling a childhood memory to solving a math problem in milliseconds. The universe employs it to funnel matter across millions of light years, seeding new stars along the way. It's as if nature stumbled upon a universal formula for building complexity, whether it's crafting a mind or sculpting a galaxy cluster. Why would such disparate systems converge on the same design? One answer lies in efficiency. Both networks evolved, whether through biological adaptation or cosmic expansion, to minimize energy waste while maximizing connectivity. Neurons conserve precious resources by forming shortcuts between distant brain regions. Similarly, the cosmic web's filaments allow gravity to work effortlessly, pulling matter into the densest regions without scattering it randomly. Another clue comes from the laws of physics themselves. Just as water finds the path of least resistance down a mountainside, complex systems, whether made of cells or dark matter, tend to self-organize into structures that follow the simplest, most stable configurations. But here's the twist. While the brain's network adapts in real time, learning and rewiring with every experience, the cosmic web changes over billions of years. Yet both are dynamic, responding to their environments in ways that preserve their core architecture. A brain injury might reroute neural pathways to compensate for damage. Likewise, when galaxies collide, the cosmic web absorbs the shock, redistributing matter along new filaments. This resilience hints at a deeper truth that complexity, at any scale, thrives on flexibility. The implications are dizzying. If the same patterns govern neurons and galaxies, could there be fundamental principles threading through all layers of reality? Some researchers speculate that these recurring structures might reveal hidden laws of information or energy flow that transcend biology and physics. Others see it as a reminder of how deeply interconnected existence truly is, that the same forces shaping the stars might also shape the way we think. Whether coincidence or cosmic inevitability, one thing's certain: the universe's grand design and the mind's inner workings are far more alike than we ever imagined. And that realization doesn't just bridge disciplines, it redefines how we see ourselves in the grand tapestry of existence. Gravity is the universe's silent sculptor, and dark matter is its chisel. In the aftermath of the Big Bang, the cosmos was a nearly smooth sea of particles, a blank canvas waiting to be shaped. But hidden within that uniformity were tiny ripples, slight variations in the density of dark matter, imperfections so small they'd seem insignificant. Yet gravity seized on these faint wrinkles, amplifying them over billions of years. Like an artist patiently carving marble, gravity transformed those subtle fluctuations into a cosmic masterpiece. Dense knots where galaxies would bloom, and vast, intertwining filaments stretching across the void. This is how the cosmic web was born, not from chaos, but from the patient, relentless pull of an invisible force. Dark matter didn't just provide the scaffolding for galaxies, it dictated their destiny. Picture a river flowing through a canyon, its path shaped by the landscape beneath it. Ordinary matter, the gas, dust, and stars we can see, behaved the same way. Drawn by the gravitational wells of dark matter, it pooled along the filaments, igniting into galaxies at their intersections. These luminous structures didn't form randomly. They followed the hidden blueprint laid out by dark matter, clustering like fireflies on an unseen web. Without this invisible guidance, galaxies might have scattered like confetti in the wind, leaving the universe a disorganized haze. Instead, we have a cosmos of breathtaking order, its grand design etched by the hand of gravity. The parallels to neural networks are impossible to ignore. Just as dark matter's gravitational tug organizes galaxies, the brain's synapses form connections guided by electrical and chemical signals. In both cases, small initial differences, whether in matter density or synaptic strength, snowball into intricate networks. A neuron doesn't randomly link to another. It follows paths of least resistance, optimizing communication. Similarly, galaxies don't drift aimlessly. They're pulled into the most efficient arrangements by gravity. It's a dance of attraction and repulsion, of forces working in harmony to build complexity from simplicity. What's truly remarkable is the timescale. While neural networks rewire themselves in seconds, the cosmic web took billions of years to assemble. Yet both systems arrived at strikingly similar architectures. This suggests something profound, that the laws governing structure and connectivity might be universal, operating the same way whether you're building a thought or a galaxy cluster. It's as if the universe has a favorite recipe for complexity, one it uses whether cooking up a brain or a supercluster. Scientists call this process hierarchical structure formation, but it's easier to think of it as cosmic teamwork. Small dark matter clumps merged into larger ones, pulling in gas and sparking the first stars. Those stars grouped into galaxies, which then clustered along filaments, creating the web we see today. Every step relied on gravity's patient, unyielding influence. And just like a spider's web gains strength from its interconnected strands, the cosmic web's resilience comes from its filaments, paths that channel matter and energy across the universe, feeding galaxies and fostering new stars. This gravitational choreography isn't just history, it's still happening. Right now, dark matter continues to shape the cosmos, guiding galaxies into ever larger clusters. The Milky Way, for instance, is being pulled toward the Andromeda galaxy, both of them destined to collide and merge in billions of years. Even on such colossal scales, the rules remain the same. Gravity draws matter together, dark matter lays the groundwork, and the cosmic web evolves. It's a reminder that the universe isn't static. It's a living, breathing entity, forever weaving itself into new patterns. So the next time you gaze at the night sky, remember, those glittering stars and distant galaxies are more than just points of light. They're the visible traces of an invisible architecture, a web spun by dark matter and sculpted by gravity. And in a strange, beautiful twist, the same forces that built the cosmos might also echo in the way your own mind connects ideas. The universe, it seems, has a signature style, and it's written in the language of networks. Supercomputer simulations are like time machines for the cosmos, powerful enough to rewind the universe back to its infancy and fast forward through billions of years of cosmic evolution in mere weeks. Projects like Illustrious TNG don't just guess at how dark matter behaves, they recreate its influence with staggering precision, weaving virtual universes where every particle of gas, every flicker of starlight, obeys the laws of physics we know. What emerges from these digital laboratories is nothing short of mesmerizing. Intricate webs of dark matter filaments stretching and knotting across the void, with galaxies blooming at their intersections like dew on a spider's silk. The resemblance to neural networks isn't just artistic, it's mathematical down to the branching patterns and the way information, or in this case, gravity, flows through the system. These simulations reveal something profound. The universe isn't just lumpy or random. It's organized with an almost eerie efficiency. Gas doesn't wander aimlessly. It's funneled along dark matter highways, pooling where the gravitational pull is strongest. Galaxies don't form in isolation. They're born into communities, linked by invisible threads that dictate their motion and growth. It's as if the cosmos has a hidden operating manual, and dark matter is the ink it's written in. Without these simulations, we'd be like ants trying to understand a skyscraper by crawling on its foundation, seeing fragments, but never the grand design. But how do we know these virtual universes reflect reality? The proof lies in the details. When astronomers compare the simulated cosmic web to real observations, like the distribution of galaxies in massive sky surveys, the patterns match with uncanny accuracy. It's not a perfect replica, of course. The universe has quirks and surprises no simulation can fully predict. Yet the broad strokes align, the filament lengths, the spacing of galaxy clusters, even the way galaxies spin within the web. This isn't just a triumph of computing power, it's validation that we're on the right track in decoding dark matter's role as the universe's master architect. What's equally fascinating is how these simulations expose the fragility of cosmic structure. Tweak the rules slightly, reduce dark matter's influence, or alter how it interacts with normal matter, and the web unravels. Galaxies scatter, filaments fray, and the elegant network collapses into chaos. This delicate balance underscores how finely tuned our universe really is. The fact that dark matter and gravity conspired to build something as intricate as the cosmic web suggests there's a deeper order at work, one that transcends scales and echoes in the neural pathways of our own minds. Perhaps the most humbling realization is that these simulations are just the beginning. Each iteration, each upgrade to computing power, peels back another layer of the mystery. Future models might reveal how dark matter drives the formation of supermassive black holes, or why some filaments glow faintly with ultraviolet light while others remain utterly dark. For now, they serve as a cosmic mirror, reflecting back not just the structure of the universe, but the ingenuity of the minds striving to understand it. And in that reflection, we glimpse a truth both simple and profound. The same patterns that bind the cosmos might also illuminate the workings of our own curiosity. Dark matter may be the invisible architect of the cosmos, but ordinary matter, the stuff we can actually see, is the artist that brings the universe to life. Think of it like a vast construction site. Dark matter erects the steel beams of the cosmic web, while baryonic matter, The protons, neutrons, and electrons that make up stars, planets, and even us fills in the walls, the wiring, the vibrant details that turn a skeleton into something alive. Without dark matter's gravitational pull, galaxies would never have clumped together. But without ordinary matter, those galaxies would just be empty shells, dark and silent. Here's how the partnership works. As dark matter's filaments weave their way across the universe, they act like cosmic rivers, guiding flows of hydrogen and helium gas along their lengths. When these streams of gas collide at the intersections of filaments, something magical happens. The gas slows, piles up, and begins to cool, shedding energy like a steaming cup of coffee left on a counter. As it cools, gravity takes over, pulling the gas into dense knots that ignite into the first stars. These stellar nurseries don't form randomly. They bloom precisely where dark matter's gravity has laid the groundwork, like flowers sprouting along the cracks of a sidewalk. But ordinary matter doesn't just passively follow dark matter's lead, it talks back. Stars don't just twinkle quietly. They explode, blow winds, and flood space with radiation. These energetic outbursts push back on the surrounding gas, heating it up and even carving bubbles in the cosmic web. It's a delicate dance, too much feedback, and galaxies would blow themselves apart before they could grow. Too little, and gas would collapse into monstrous black holes without ever forming stars. The fact that we exist at all suggests a Goldilocks balance, one where ordinary matter and dark matter have negotiated a cosmic truce, allowing galaxies like our Milky Way to thrive. This interplay isn't so different from how neurons and glial cells cooperate in your brain. Neurons, the flashy stars of the nervous system, send electrical signals, but they rely on glial cells to nourish them, clean up waste, and even fine-tune their connections. Neither can function alone. In the same way, dark matter provides the cosmic infrastructure, but it's ordinary matter that lights up the universe, turning gravity's blueprint into a living, evolving masterpiece. And just like the brain adapts to new experiences, the cosmic web evolves with time. Early galaxies were messy and chaotic, churning out stars in fits and bursts. But as the universe aged, gas flows became more regulated, settling into the elegant spiral arms and serene disks we see today. Dark matter's scaffolding didn't change much, it's the patient, steady hand. But ordinary matter learned to work with it, optimizing star formation and building planets capable of harboring life. So when you look up at the night sky, remember, every star, every nebula, every flicker of light is part of a grand collaboration. Dark matter may have drawn the map, but ordinary matter is the traveler, the one that took the journey, filled in the blanks, and turned the universe from a shadowy sketch into a breathtaking portrait. And in that partnership, we find the most astonishing truth of all. The same forces that lit the stars also lit the spark of curiosity in our own minds. Galaxy clusters are the metropolises of the cosmos, dense, bustling hubs where thousands of galaxies gather like commuters at a grand central station. But unlike cities built on solid ground, these clusters hang suspended at the intersections of dark matter filaments, held together by the invisible threads weaving through the universe. Picture the cosmic web as a subway system with dark matter acting as the tracks. Where multiple lines cross, you get a major transit hub, and in the universe's case, that's where galaxy clusters form, pulling in matter from all directions like a gravitational whirlpool. What makes these clusters so fascinating isn't just their size, though some span tens of millions of light years. It's how they reveal the hidden architecture of the cosmos. Just as studying traffic patterns in a city can expose the layout of its roads, observing how galaxies move within clusters allows astronomers to reverse engineer the dark matter scaffolding beneath them. The speeds at which galaxies orbit, the way they're distributed, even the way hot gas glows between them, All of these are clues pointing to the presence of an unseen gravitational anchor, far more massive than anything we can detect with telescopes. Here's where the neural network comparison gets even more intriguing. In the brain, information flows most intensely at the nodes where many neurons connect. Similarly, galaxy clusters are where the cosmic web's activity concentrates. Rivers of gas stripped from galaxies during collisions stream along filaments into these dense knots, fueling new star formation or feeding supermassive black holes. Some clusters even become cosmic power plants, pumping out vast amounts of energy as galaxies merge and black holes devour matter. It's a dynamic, almost alive system, one that mirrors the way electrical signals amplify at key junctions in the brain. But there's a twist. Galaxy clusters aren't just passive waypoints. They actively reshape their surroundings. The immense gravity of a cluster bends space-time itself, warping the path of light from more distant galaxies in a phenomenon called gravitational lensing. This creates surreal, stretched images of background objects, nature's way of letting us peek at the universe's hidden scaffolding. Some clusters even act as cosmic telescopes, magnifying faint galaxies so far away they'd otherwise be invisible. It's as if the universe handed us a tool to see its own blueprint. The story of galaxy clusters is also a story of cosmic evolution. In the early universe, these hubs were smaller and more chaotic, like fledgling towns without clear infrastructure. Over billions of years, they grew by merging with neighboring clusters, their dark matter halos colliding and intertwining in a slow-motion ballet. Today, we see the results: sprawling megastructures like the Coma cluster, home to over 1,000 galaxies, or the Bullet cluster, where a violent collision left dark matter visibly separated from hot gas, a smoking gun proving dark matter's existence. What's remarkable is how these clusters preserve a record of the universe's history. Much like tree rings encode centuries of growth. By studying their composition, temperature, and motion, astronomers can trace how dark matter guided the cosmos from a smooth primordial soup to the intricate web we see today. And just as neurons strengthen connections through repeated use, galaxy clusters grow more defined over time, their gravitational pull drawing in ever more matter, refining the universe's grand design. So the next time you hear about a distant galaxy cluster, remember, you're not just looking at a random clump of stars, you're witnessing a cosmic crossroads, a place where the universe's hidden architecture becomes visible, where dark matter's whisper finally grows loud enough to hear. And in understanding these hubs, we're not just mapping the cosmos, we're deciphering the very rules that built it. Voids are the universe's silent deserts, expanses so empty, so stark, that if you stood in the middle of one, the nearest galaxy would be millions of light years away. These cosmic blank spots aren't accidents. They're the flip side of the cosmic web's intricate design. Just as neurons cluster together with gaps between them, dark matter's gravitational push has sculpted the universe into a sponge-like structure, with dense filaments surrounding hollowed-out regions. But don't mistake these voids for nothingness. They're not empty, they're evolved. Inside a void, space isn't just black and barren. Thin strands of gas stretch like ghostly bridges, and a handful of lonely galaxies drift like ships in an endless ocean. These isolated galaxies are often misfits, small, faint, and strangely shaped, as if the void itself has starved them of the cosmic camaraderie that fuels star formation in denser regions. Without the gravitational jostling of neighboring galaxies, they age quietly, their gas reservoirs untapped, their stellar nurseries shut down. It's a galactic retirement home where time moves slower and change comes rarely. What's fascinating is how these voids form. In the early universe, dark matter didn't just pull matter together, it also pushed it apart. Tiny regions with slightly less density than their surroundings acted like cosmic repellers. As gravity amplified denser areas into filaments and clusters, these underdense zones expanded, their gravitational weakness creating a kind of anti-attraction. Matter flowed away, draining into the web's bustling intersections and leaving behind these vast, ever-growing bubbles. The largest voids can span hundreds of millions of light-years, making them some of the biggest structures in existence, yet they're defined by what's not there. Studying voids is like reading the universe's negative space. By measuring their shapes and sizes, astronomers can trace the invisible hand of dark matter. If filaments are the cosmic web's threads, voids are the holes in its fabric, and the way those holes stretch and distort reveals the tension of the weave. For instance, some voids appear slightly squashed, their edges sharper in one direction than another. That asymmetry hints at the gravitational tug of war between neighboring superclusters, a subtle warping that wouldn't be visible without mapping the emptiness between them. But voids aren't just passive byproducts, they actively shape the universe's expansion. Inside these regions where gravity's grip is weakest, dark energy, the mysterious force accelerating the cosmos, works unimpeded. Space here stretches faster, as if the void itself is breathing outward. Over time, this relentless push may even tear the cosmic web apart, unraveling filaments like a sweater caught on a nail. Some scientists believe voids hold the key to understanding dark energy's ultimate influence, offering a preview of how the universe might end, not with a bang, but with a slow, silent dissipation into ever larger nothingness. Yet for all their emptiness, voids have a strange beauty. They remind us that the universe's structure depends as much on absence as presence. Without these hollows, galaxies would crowd together like trees in an overgrown forest, leaving no room for the grand patterns we see. The cosmic web needs its gaps just as a painting needs its shadows, not as flaws, but as essential contrasts that give the whole its depth. So the next time you look up at the night sky, remember, the darkness between the stars isn't just empty space. It's part of the universe's hidden architecture, a silent testament to the forces that shaped everything including us. Galaxies spin like cosmic carousels, with stars whirling around their centers in a delicate gravitational ballet. But here's the puzzle. The speed at which these stars orbit doesn't match what we'd expect if only visible matter, stars, gas, and dust were pulling the strings. According to Newton's laws, stars on the outer edges of a galaxy should move slower, just like planets farther from the sun orbit at a more leisurely pace. Yet when astronomers measure galactic rotation curves, they find something startling. Stars at the fringe race just as fast as those near the core, defying gravity's usual rules. The only explanation, an invisible hand must be at work, adding extra gravitational glue to hold galaxies together. That hand belongs to dark matter. This discrepancy between prediction and reality isn't just a minor hiccup, it's a cosmic clue written in starlight. Without dark matter's gravitational embrace, galaxies would spin themselves apart, flinging stars into the void like sparks from a wheel. The outer stars, moving at breakneck speeds, would escape their galactic homes entirely, but thanks to dark matter's vast, diffuse halo enveloping each galaxy, those stars stay anchored. Think of it like a hidden safety net, stretching far beyond the galaxy's luminous disk, its gravity gently tugging on every star to keep the system intact. The comparison to neural myelin sheaths is almost poetic. In your brain, these fatty layers wrap around nerve fibers, insulating electrical signals so they don't dissipate before reaching their destination. Without myelin, impulses would sputter out, leaving thoughts fragmented and movements uncoordinated. Dark matter plays a similar role for galaxies. It's the cosmic insulator, ensuring gravitational signals the pull holding stars in orbit remains strong and consistent across vast distances. Both systems rely on an unseen stabilizer, one biological, the other astrophysical, yet both essential for maintaining order in their respective realms. What's even more fascinating is how this dark matter halo isn't just a static shell, it's dynamic, responding to the galaxy's evolution. As galaxies merge or cannibalize smaller neighbors, their dark matter halos grow and reshape, like a living organism adapting to its environment. Simulations show these halos aren't smooth spheres either. They're lumpy, strewn with subhalos, smaller clumps of dark matter that survived the galaxy's formation. Some researchers believe these subhalos could host failed galaxies, collections of stars too faint to see, orbiting like ghosts in the cosmic night. The implications stretch beyond just keeping galaxies from flying apart. Dark matter's influence on rotation curves reveals how deeply it's woven into the fabric of galactic life. It dictates where stars form, how gas flows, even how galaxies interact with their neighbors. Without it, the universe would look utterly different. No grand spirals, no majestic ellipticals, just scattered stars adrift in a sea of darkness. So the next time you see an image of a whirling galaxy, remember, what you're seeing is only a fraction of the story. The rest is written in the silent, steady pull of the unseen. Feedback loops are nature's way of keeping things in check, a cosmic thermostat ensuring systems don't spiral out of control. Take your brain. Every time you learn something new, neurons fire in specific patterns, and the connections between them grow stronger. Repeat a skill often enough, and those pathways become highways optimized for speed and efficiency. But here's the catch: if a neural pathway goes unused, it weakens over time, pruned away to make room for more active connections. This constant give and take, known as synaptic plasticity, is the brain's feedback loop, fine-tuning itself with every thought and action. Now, zoom out to the cosmic scale, and you'll find eerily similar mechanisms at play. Supermassive black holes lurking at the hearts of galaxies aren't just passive monsters, they're active regulators. When a black hole feasts on surrounding gas, it doesn't do so quietly. It belches out colossal jets of energy and radiation, heating up the galaxy's gas reservoir like a cosmic blowtorch. This energy injection pushes back against gravity's pull, preventing too much gas from collapsing into stars all at once. Without this feedback, galaxies would burn through their fuel in a frenzy of star formation, leaving behind a lifeless husk. Instead, black holes act like galactic pacemakers, keeping star birth at a sustainable rhythm. Supernova exploding stars play a similar role. When a massive star reaches the end of its life, it detonates with the force of 1 billion suns, scattering heavy elements into space and blasting shockwaves through surrounding gas clouds. These shockwaves can compress nearby gas, triggering new star formation, or they can disperse it, putting a temporary halt to stellar births. It's a self-regulating cycle. Stars create the conditions for their own successors, but also the forces that limit them. What's striking is how these feedback loops mirror the brain's balancing act. Just as neurons adjust their connections based on activity, galaxies adjust their growth based on energy flows. Too much star formation, black holes and supernova dial it back. Too little, gravity takes the lead, pulling gas back into the dance. Both systems thrive on equilibrium, where stability isn't static, it's a dynamic tug of war between opposing forces. The implications are profound. Feedback loops don't just maintain balance, they shape evolution. In the brain, they allow learning and adaptation, turning fleeting experiences into lasting memories. In the cosmos, they dictate how galaxies mature, determining whether they become vibrant spirals or dormant ellipticals. And just as the brain's plasticity declines with age, galaxies too seem to slow their star formation over billions of years, settling into a quieter existence. Perhaps the most fascinating parallel is how both systems handle extremes. In the brain, an overactive feedback loop can lead to conditions like epilepsy, where neurons fire uncontrollably. In galaxies, unchecked black hole growth can produce quasars' luminous beacons so bright they outshine entire galaxies. Yet both systems have built-in safeguards. The brain has inhibitory neurons to calm excessive activity, while galaxies rely on those very energy outbursts to cool their fervor. It's as if the universe and the mind share a playbook for resilience, written in the language of feedback. So whether it's a neuron adjusting its strength or a black hole regulating its feast, the message is clear: balance isn't an accident. It's a carefully negotiated truce, a dance of push and pull that keeps both minds and galaxies from tipping into chaos. And in that delicate equilibrium, we find yet another thread connecting the vast cosmos to the intricate workings of our own thoughts. Fractal patterns are nature's signature, repeating designs that echo across scales, from the microscopic to the cosmic. Take a snowflake, its delicate branches split into smaller branches, each one a miniature replica of the whole. Zoom out to a river delta, and you'll see the same branching motif etched into the landscape, as if the universe has a favorite blueprint it can't stop reusing. Now stretch your gaze further to the cosmic web's filaments, threading through the void like veins in a leaf, or to the dendritic branches of neurons firing inside your skull. The resemblance isn't just visual, it's mathematical. These structures share a hidden language, one governed by fractal geometry, a pattern where the same shape repeats itself, no matter how far you zoom in or out. What's mesmerizing is how these fractals emerge without a master plan. No cosmic architect sketched the universe's web or the brain's neural tangles. Instead, simple rules: gravity pulling matter into filaments, electrical signals optimizing neural pathways, give rise to complexity that feels almost artistic. It's as if nature has a toolkit of fractal algorithms, deploying them wherever efficiency and resilience are needed. In the brain, fractal branching maximizes surface area, packing more connections into limited space. In the cosmic web, it allows gravity to distribute matter evenly, avoiding clumps that would collapse under their own weight. The same design solves different problems, yet the outcome is uncannily similar. This fractal echo raises a tantalizing question. Could there be a universal principle at work, one that transcends biology and physics? Some scientists speculate that fractals hint at deeper laws, perhaps even a shared mechanism for how information or energy flows through complex systems. Think of it like this: whether it's electricity racing through a neuron or gravity tugging gas along a cosmic filament, both systems are channeling something: a signal, a force along the path of least resistance. Fractals might be nature's way of optimizing that flow, a recurring solution to the puzzle of building complexity from simplicity. The evidence isn't just poetic, it's measurable. Researchers have compared the branching patterns of cosmic filaments to neural networks and found their fractal dimensions, a mathematical measure of complexity, are nearly identical. Even more startling, the distribution of galaxies along filaments mirrors the spacing of synapses in the brain. This isn't just coincidence, it's a clue that the universe and the mind might be playing by the same rules, written in the language of fractals. But why would nature favor this design? One answer lies in efficiency. Fractals balance chaos and order, creating structures that are both flexible and robust. A neuron's branches can adapt to new connections without rewiring entirely. Similarly, the cosmic web can absorb collisions between galaxy clusters without unraveling. Another advantage is scalability. Fractals work just as well for a single neuron as they do for a galaxy-spanning filament. It's a design that grows with the system, no matter how vast or minute. The implications ripple beyond science. If the universe and the brain share a fractal blueprint, it challenges how we define connection. Are these patterns mere accidents of physics, or is there something deeper, a unity hidden in plain sight? For now, the fractal mystery remains unsolved, but every discovery pulls us closer to a staggering possibility that the cosmos and consciousness might be more alike than we ever dared imagine. And in that symmetry, we find not just wonder, but a humbling reminder of how deeply we're woven into the fabric of existence. In the beginning, the universe was a nearly featureless expanse, a smooth, hot soup of particles so uniform that if you blinked, you might miss the subtle ripples lurking within. But those faint wrinkles, those tiny variations in density, held the seeds of everything to come. Dark matter, already present in those primordial moments, began its quiet work. Wherever there was even a whisper more of it, gravity leaned in, pulling particles closer, amplifying the difference. Over millions of years, what started as microscopic imperfections grew into vast gravitational wells, drawing in gas like water swirling down a drain. This slow, relentless process, hierarchical structure formation, built the universe piece by piece, from scattered atoms to glittering galaxies. What's astonishing is how closely this mirrors the way our own brains learn and grow. Just as dark matter's gravity sculpted the cosmos incrementally, neural networks strengthen connections through repetition and feedback. A child learning to walk doesn't master balance in a day. Their brain reinforces successful movements while pruning the missteps. Similarly, the cosmic web didn't spring into existence fully formed. It assembled itself step by step, with smaller dark matter clumps merging into larger ones, galaxies grouping into clusters, and filaments threading it all together. Both systems, cosmic and cognitive, embrace trial and error, refining their structures over time to achieve stability. The early universe was a laboratory of simplicity. Dark matter's initial clumps were no larger than Earth's mass, yet they became the scaffolding for structures a billion times bigger. Gas, attracted by these invisible anchors, cooled and condensed, igniting the first stars in fiery bursts. These stars then grouped into proto-galaxies, which collided and merged, growing into the majestic spirals and ellipticals we see today. It's a story of accumulation, where gravity's patience transformed cosmic whispers into a symphony of light. Neural networks follow a strikingly similar script. A newborn's brain starts with a surplus of connections, a chaotic tangle of potential. Through experience, some synapses strengthen, like gravity pulling matter into denser regions, while others fade away, like gas scattered by supernova shocks. This pruning isn't destruction, it's refinement. Just as the cosmic web's filaments grew clearer as stray matter settled into place, the brain's pathways sharpen with use, optimizing for efficiency. Both systems trade initial randomness for elegant order, proving that complexity often arises from the simplest rules repeated over time. Yet there's a crucial difference in scale. While the brain rewires itself in days or weeks, the cosmic web took billions of years to mature. Imagine if every thought you had left a permanent mark on your neurons, visible for eons. That's the universe's reality. Its growth is etched into space-time itself, a slow-motion masterpiece we're only now learning to read. And just as neuroscientists study brain development to understand disorders, cosmologists trace the universe's evolution to solve mysteries like dark matter's true nature. Both quests hinge on recognizing patterns, whether in the flicker of a synapse or the spin of a galaxy. This parallel isn't just academic. It's a reminder that the universe and the mind might share deeper operating principles. Perhaps the same mathematical laws that govern gravitational collapse also guide how information organizes itself in networks, from neurons to ecosystems to galaxies. If so, then studying one could illuminate the other, bridging the gap between astrophysics and artificial intelligence. After all, if dark matter can build a universe, what might its hidden rules teach us about building better machines, or even understanding consciousness itself? The answers, like the early cosmos, are still taking shape, one discovery at a time. The mystery of dark matter's composition is one of the most tantalizing puzzles in modern science. We know it's out there. Its gravitational fingerprints are all over the cosmos, but what exactly is it? Imagine knowing someone only by their shadow, glimpsing their influence without ever seeing their face. That's the frustration physicists face with dark matter. It makes up 85% of the universe's matter, yet it refuses to show itself directly. So what are the leading suspects in this cosmic whodunit? One prime candidate is WIMP, weakly interacting massive particles. These hypothetical particles are thought to be heavy, slow-moving, and, as their name suggests, incredibly shy. They'd rarely bump into ordinary matter, explaining why we haven't detected them yet. If WIMP exist, they could be everywhere around us, streaming through your body right now like ghosts passing through walls. Scientists have built ultra-sensitive detectors deep underground, shielded from cosmic noise, hoping to catch a WIMP faint whisper of interaction. So far, no luck. But the hunt isn't over, it's just getting more creative. Then there's the Action, a featherweight contender born from an entirely different puzzle in particle physics. Actions would be billions of times lighter than electrons, slipping through detectors like mist through a sieve. But their sheer numbers could make up for their shyness, collectively exerting enough gravitational pull to explain dark matter's effects. Recent experiments, like the Action dark matter experiment, use powerful magnetic fields to coax these elusive particles into revealing themselves. It's like trying to catch smoke with a magnet, but if it works, it could crack the case wide open. But here's the twist: dark matter might not be one thing at all. Some theories suggest a mix of particles, like a cosmic soup with multiple ingredients. Others propose something even stranger: primordial black holes, forged in the chaos of the early universe, lurking unseen in the voids between stars. Or perhaps dark matter isn't matter at all, but a quirk of gravity itself, a shadowy side effect of how space-time curves on cosmic scales. Each possibility would rewrite the rules of physics, reshaping our understanding of everything from galaxy formation to the birth of the universe. What makes this search so electrifying isn't just the thrill of discovery, it's the ripple effects. If dark matter is WIMP, it could mean undiscovered forces and particles waiting to be found. If it's Actions, it might solve two mysteries at once, tying dark matter to other gaps in our quantum theories. And if it's something entirely new, well, that's where the real fun begins. Every time we rule out an option, the remaining possibilities become stranger, more exotic, pushing the boundaries of what we thought was possible. This isn't just about filling a gap in our equations. Dark matter's identity shapes the cosmic web's very architecture. Different particles would clump differently, altering how filaments form and galaxies emerge. It might even hint at connections to neural networks. If the same math governs both, could the particles behind dark matter also influence how information flows in the brain? Far-fetched, maybe, but in a universe where galaxies mirror neurons, it's worth wondering. So while we don't have answers yet, the search itself is a testament to human curiosity. Every null result, every clever experiment, brings us closer to unveiling the universe's biggest secret. And when we finally do, it won't just solve a cosmic riddle, it'll reveal the hidden hand that sculpted everything we see and everything we are. Not everyone is convinced dark matter is the missing piece of the cosmic puzzle. A small but passionate group of physicists argue we've been looking at the problem backward, that instead of an invisible substance tugging on galaxies, gravity itself might play by different rules when you zoom out to interstellar distances. This radical idea, known as modified Newtonian dynamics or MUND, suggests that Newton's centuries-old laws, while flawless in our solar system, need tweaking to explain why galaxies rotate faster than expected. Imagine gravity as an old radio perfectly tuned for nearby stations, but needing a slight adjustment to pick up distant signals clearly. MUND's appeal lies in its simplicity. By modifying how gravity behaves at extremely low accelerations, like those at a galaxy's outer edges, it can replicate dark matter's effects without invoking mysterious particles. Picture a car that inexplicably speeds up when you take your foot off the gas. Instead of inventing an invisible pedal pusher, MUND proposes the engine's rules change at low speeds. Early successes seemed promising. MUND accurately predicted the rotation curves of many galaxies using just visible matter, no dark stuff required. For supporters, this was Occam's razor in action, a cleaner solution that didn't rely on undiscovered physics. But the cosmic web complicates this elegant picture. While MUND might explain individual galaxies, it struggles to recreate the universe's large-scale structure. Those sprawling neural network-like filaments where galaxies cluster like fireflies on a spider's silk. Simulations show that without dark matter's gravitational scaffolding, the cosmos wouldn't weave itself into such intricate patterns. It's like trying to build a suspension bridge with only half the cables. The design collapses under its own ambition. The web's delicate balance of voids and filaments points overwhelmingly to an invisible mass gently herding ordinary matter into place over billions of years. Even more damning for MUND are observations of colliding galaxy clusters, like the famous Bullet cluster. Here, two clusters smashed together so violently that their gas clouds packed with ordinary matter got stuck in the middle like cosmic traffic jam. Meanwhile, gravitational lensing revealed most of the mass had sailed ahead, parting ways with the visible material. If MUND were correct, the lensing effect should have followed the gas, not raced ahead. Instead, it looked exactly like dark matter's signature, an invisible mass moving independently, unfazed by the collision. The debate isn't just academic, it cuts to the heart of how science progresses. Dark matter proponents argue that modifying gravity is like adding epicycles to planetary orbits, a clunky fix that avoids admitting we're missing something fundamental. MUND advocates counter that doubling down on an undetected particle for 80 years is the real stubbornness. Yet intriguingly, some theorists now explore hybrid models where both ideas coexist. Perhaps gravity behaves oddly and dark matter exists. A cosmic compromise that could explain anomalies neither theory solves alone. What's undeniable is how this rivalry pushes science forward. Every challenge to dark matter forces researchers to sharpen their predictions, design better tests, and dig deeper into the universe's hidden layers. Whether the answer lies in unseen particles or rewritten laws of physics, one thing's certain: the cosmos still holds secrets that defy our simplest assumptions. And in that tension between the known and the unknown, we find the thrill of discovery itself. Machine learning is turning astronomy inside out, revealing hidden patterns in the cosmos that even the sharpest human eyes would miss. Picture this: every night, telescopes around the world capture terabytes of data, millions of galaxies, each a smudge of light holding secrets about dark matter's grip. Sifting through this avalanche of information manually would take lifetimes, but artificial intelligence chews through it in hours, spotting connections no one thought to look for. It's like giving a detective a magnifying glass that can see through walls suddenly. the invisible becomes visible. One of AI's most stunning feats is mapping dark matter without ever directly detecting it. By analyzing how light bends around galaxies, a phenomenon called gravitational lensing, machine learning algorithms reconstruct the unseen mass-warping spacetime behind the scenes. Traditional methods required painstaking manual measurements, but neural networks trained on millions of simulated universes now do it automatically. They've uncovered dark matter filaments so faint they were once written off as noise, filling in gaps in the cosmic web like a painter restoring a faded masterpiece. But AI's cosmic talents don't stop there. Take galaxy clusters, the universe's bustling metropolises. Identifying them in telescope images used to mean astronomers squinting at screens, debating whether a clump of pixels was a true cluster or just a chance alignment. Now, algorithms scan entire sky surveys, flagging clusters with superhuman accuracy. Some even predict how these clusters will collide and merge billions of years from now, like celestial fortune tellers reading the gravitational tea leaves. The irony is delicious. The same technology inspired by neural networks is now decoding a universe that eerily resembles them. Machine learning thrives on finding patterns, and the cosmos serves up fractal designs on a galactic platter. When an AI analyzes the cosmic web, it's not just processing data. It's staring into a mirror, recognizing the same branching logic that powers its own circuits. This feedback loop between artificial and cosmic networks hints at something profound, that the rules of connectivity might transcend silicon, synapses, and spacetime itself. Yet the real magic lies in how these tools are transforming discovery. AI doesn't replace astronomers, it amplifies them. By handling the grunt work of data crunching, it frees scientists to ask bigger questions, like why certain galaxies defy dark matter's pull, or how the cosmic web structure influences star formation. It's as if we've been handed a universal translator, decoding the universe's hidden language one algorithm at a time. And with every pixel analyzed, every filament mapped, we're not just learning about dark matter, we're uncovering the invisible threads that stitch reality together. The cosmic microwave background is the universe's oldest photograph, a hazy glow from a time when everything was compressed into a seething plasma, just 380,000 years after the Big Bang. This afterglow isn't just ancient light, it's a fossilized imprint of the cosmos in its infancy, capturing the faintest wrinkles in spacetime itself. And hidden within those wrinkles lies dark matter's earliest signature, subtle variations in density that would one day blossom into galaxies, clusters, and the vast filaments of the cosmic web. It's as if we're holding a baby picture of the universe, where the shadows already hint at the adult it will become. What makes the CMB so extraordinary is how it preserves these primordial fluctuations with near-perfect fidelity. Imagine blowing up a balloon with tiny dots painted on its surface. As the balloon expands, the dots spread apart, but their relative positions stay the same. The CMB works similarly. It's stretched with the expanding universe, locking those early density variations into place like cosmic fingerprints. Dark matter's gravitational pull amplified these faint ripples over billions of years, sculpting them into the grand structures we see today. The same way a single strand of DNA holds the blueprint for an entire organism, these temperature variations, some just one part in 100,000, encoded the universe's future architecture. Scientists decode this celestial cipher using instruments like the Planck satellite, which mapped the CMB's temperature variations with microscopic precision. Warmer spots correspond to slightly denser regions where dark matter's gravity had already begun pooling matter. Cooler patches mark the embryonic voids. When researchers compare these maps to today's cosmic web, the connection is undeniable. the largest galaxy clusters trace back to the warmest CMB spots, while vast cosmic deserts align with the coldest. It's a staggering continuity, linking the universe's first whispers to its present-day roar. The parallels to brain development are almost eerie. Just as the CMB's fluctuations set the stage for galactic filaments, the human brain's initial neural wiring follows genetic and chemical gradients that guide where connections form. Both systems start with a simple code, cosmic or biological, that unfolds into staggering complexity through time and interaction. The key difference: the universe had billions of years to grow, while your brain built its networks in mere decades. Yet both processes rely on the same principle: tiny initial differences, magnified by natural forces, creating order from chaos. But the CMB isn't just a relic, it's a Rosetta Stone for dark matter's properties. By measuring how those primordial ripples propagate, physicists can calculate dark matter's temperature, or how fast its particles were moving in the early universe. Cold dark matter, slow-moving and heavy, would clump differently than hot dark matter, fast and lightweight. The CMB's patterns overwhelmingly favor the cold scenario, explaining why galaxies could form so efficiently. It's like deducing the shape of an invisible sculptor by studying the grooves they left in clay. This snapshot also reveals the cosmic web's surprising adolescence. Some filaments appear to have formed earlier than expected, their shadows already visible in the CMB's subtle distortions. Gravitational lensing, where the web's mass bends the CMB light, lets astronomers trace dark matter's distribution at different cosmic epochs, effectively creating a time-lapse of the universe's growth. The result: a dynamic portrait where dark matter doesn't just underpin the cosmos, it conducts its evolution, with the CMB as its opening note. So when you see those grainy, rainbow-colored maps of the CMB, remember, you're not looking at static noise. You're witnessing the first strokes of a masterpiece, the moment dark matter began weaving the universe into existence. And just as archaeologists piece together civilizations from pottery shards, cosmologists use this ancient light to reconstruct the cosmos' grand narrative, one fluctuation at a time. Galaxy filaments are the universe's ultimate superhighways, vast, twisting rivers of dark matter and gas that stretch across the cosmos, guiding galaxies toward their gravitational destiny. Think of them as cosmic express lanes, where entire galaxies hitch rides along these invisible currents, pulled by the relentless tug of dark matter's gravity. The sheer scale is staggering. Take the Hercules Corona Borealis Great Wall, the largest known filament, spanning an almost incomprehensible 10 billion light-years. To put that in perspective, if our Milky Way were a single grain of sand, this filament would be longer than the entire Amazon River. What's mesmerizing about these filaments isn't just their size, it's how they function. Like neural pathways in a brain, they don't just connect points, they direct traffic. Gas streams along these filaments, cooling and condensing as it travels, fueling star formation in the galaxies that call these corridors home. Where filaments intersect, you'll find bustling galactic metropolises, clusters teeming with thousands of galaxies, drawn together like cars merging onto a freeway interchange. These junctions are the universe's power hubs, where collisions ignite quasars and supermassive black holes feast on swirling gas. But filaments aren't static. They pulse with activity, responding to the ebb and flow of cosmic forces. When galaxies collide, shockwaves ripple through the surrounding filaments, sending tremors across millions of light-years. Sometimes filaments even snap, their gravitational ties severed by the relentless expansion of the universe, leaving galaxies stranded in the void like cars abandoned on a deserted highway. Yet even in their destruction, filaments shape the cosmos. The gas they leave behind becomes the raw material for future galaxies, ensuring the cycle of creation never ends. The resemblance to neural networks isn't just metaphorical, it's mathematical. Just as your brain's axons optimize signal efficiency, minimizing energy loss as thoughts race between neurons, cosmic filaments follow the same principle. They're nature's solution to moving matter across impossible distances with minimal wasted effort. Gravity does the heavy lifting, but the design, the way filaments branch, thicken, and thin mirrors the same pattern seen in everything from lightning bolts to the veins in a leaf. It's as if the universe has a playbook for building networks, whether it's transmitting electricity or shepherding galaxies. Here's where it gets even wilder. Filaments might hold the key to the universe's expansion. Their immense gravity tugs on surrounding space, slowing the spread of galaxies in some regions while dark energy stretches others apart. By mapping these cosmic thoroughfares, astronomers can trace how the universe has grown over billions of years, like reading tree rings in a galactic redwood. Each filament is a time capsule, preserving the history of everything it's carried: stars, gas, even the seeds of life itself. So the next time you gaze at a starry sky, remember, those glittering dots aren't just scattered randomly. They're travelers on an invisible highway, part of a network so vast it makes every road on Earth look like a speck of dust. And just as neural pathways shape our thoughts, these filaments shape the universe's destiny, one galaxy at a time. Dark matter may be the unseen glue holding galaxies together, but there's another cosmic phantom working in opposition: dark energy, the mysterious force ripping the universe apart at the seams. Imagine a cosmic tug of war where dark matter's gravity pulls galaxies into filaments and clusters, weaving the cosmic web tighter, while dark energy stretches spacetime itself, pushing those same filaments farther apart. This silent battle between attraction and repulsion doesn't just shape the universe's structure, it dictates its ultimate fate. For centuries, scientists assumed gravity would eventually slow the universe's expansion, like a ball tossed upward, gradually losing momentum. Then, in the late 1990s, astronomers made a startling discovery. By measuring distant supernova, they found the universe wasn't just expanding, it was accelerating, as if some invisible force had slammed its foot on the cosmic gas pedal. That force, dark energy, a phenomenon so perplexing it makes dark matter seem straightforward by comparison. Unlike dark matter, which clumps and tugs, dark energy appears perfectly smooth, permeating every corner of space with a gentle but relentless push. The cosmic web is caught in this crossfire. Dark matter's gravity builds the scaffolding, pulling galaxies into filaments and clusters, while dark energy stretches the space between them, thinning the web over time. In regions where dark matter's grip is strongest, like galaxy clusters, gravity wins, holding structures together even as the universe expands. But in the voids, those vast cosmic deserts where matter is scarce, dark energy reigns unchallenged, accelerating the emptiness's growth until some filaments may eventually snap, stranding galaxies in isolation. This interplay creates a universe of contrasts. Picture a rubber sheet dotted with weights. The weights are galaxy clusters, warping the sheet with their gravity, while someone steadily stretches the sheet's edges outward. The weights resist the stretching, staying clustered together, but the space between them grows ever wider. That's our cosmos, islands of matter holding fast as the void around them inflates. Over billions of years, this could lead to a Big Rip scenario, where dark energy's dominance tears apart everything from galaxies to atoms, or a Big Chill, where expansion leaves the universe cold, dark, and eerily empty. Yet dark energy isn't just a destructive force. Without it, the cosmic web might have collapsed long ago, its filaments crumpling under dark matter's pull into a dense, chaotic knot. Instead, the tension between these two invisible giants maintains a dynamic balance. allowing structures to form while keeping the universe from imploding or flying apart too soon. It's a delicate dance, one that's lasted 13.8 billion years and will continue until one force finally gains the upper hand. The key to predicting the winner lies in understanding dark energy's nature. Is it a constant force, as Einstein's cosmological constant suggested? Or does it evolve over time, growing stronger or weaker? Current observations favor the former, but even a slight change could alter the universe's destiny. If dark energy strengthens, it might one day overpower even galaxy clusters, shredding the cosmic web entirely. If it weakens, dark matter's gravity could regain dominance, pulling the universe back into a big crunch. For now, the cosmic web persists, a testament to the fragile equilibrium between these two shadowy titans. And as astronomers map ever more distant filaments and voids, they're not just charting the universe's structure, they're reading the tea leaves of its ultimate fate, written in the invisible ink of dark energy and dark matter. The universe plays a breathtaking game of scale, where the rules governing the tiniest particles somehow echo in the grandest cosmic structures. Zoom into the quantum realm, where particles flicker in and out of existence in a probabilistic dance, and you'll find the same mathematical elegance that describes the gravitational tango of galaxy clusters. Dark matter is the silent bridge between these extremes, a hidden thread stitching together the microscopic and the cosmic. It's as if nature has a secret language, one where the same patterns repeat, whether you're observing the behavior of subatomic particles or the sprawling filaments of the cosmic web. This multiscale harmony isn't just poetic coincidence, it's a clue to how the universe organizes itself. Consider a single neuron in your brain, a microscopic cell pulsing with electrical signals, seemingly insignificant on its own. Yet when billions of these neurons connect, their collective activity gives rise to thoughts, memories, even consciousness itself. Dark matter operates in a similar way. Individually, its particles, whatever they may be, are faint, elusive, barely interacting with the world we know. But en masse, their gravitational influence orchestrates the birth of galaxies, the weaving of cosmic filaments, the very architecture of reality. The small becomes large, the invisible becomes undeniable. The parallels run deeper than mere metaphor, just as neural networks rely on synaptic strength. The way some connections between neurons grow stronger with use, dark matter's influence depends on density. Where its particles cluster slightly tighter, gravity pulls harder, sculpting the seeds of future galaxies. These tiny initial imbalances, magnified over billions of years, become the cosmic web's grand nodes and threads. It's a feedback loop of scale. Quantum fluctuations in the early universe snowball into galactic superstructures, much like how a single thought can trigger a cascade of neural activity, lighting up entire brain regions. What's truly humbling is how this interconnectedness challenges our intuition. Human brains evolved to perceive the world at human scales, objects we can touch, distances we can walk. The idea that the same underlying principles might govern everything from quarks to quasars feels almost alien, yet the evidence is everywhere. Fractal patterns in tree branches mirror the branching of cosmic filaments. Turbulent flows in water resemble the swirling arms of galaxies. Even the distribution of matter in the universe follows power laws, mathematical relationships that appear in everything from earthquake magnitudes to the frequency of words in language. Dark matter's role in this multiscale symphony is still being deciphered, but one thing is clear: it doesn't just fill the gaps in our theories. It reveals a universe far more deeply linked than we ever imagined, where the very small and the unimaginably large are two sides of the same coin. And in that revelation, we find a profound truth that to understand the cosmos, we might also need to understand the mind, and vice versa. The universe, it seems, is less a collection of separate things than a single, shimmering network, vibrating across all scales at once. Biological and cosmic evolution share a rhythm, a slow, relentless march toward complexity that plays out across wildly different scales. Your brain didn't spring into existence fully formed. It grew, adapting over millions of years, with synapses firing, strengthening, and sometimes fading away as experiences shaped its architecture. Now, lift your gaze to the cosmos. Galaxies, too, evolve over epochs, merging and colliding, their structures growing richer with time. The Milky Way wasn't always the grand spiral we know today. It's a product of countless collisions, absorbing smaller galaxies like a cosmic sponge, its shape shifting with each encounter. The parallels between these processes, neural and galactic, aren't just poetic. They hint at something deeper, universal laws of growth that transcend the boundaries of biology and physics. Consider how a child learns to ride a bike. At first, their brain fumbles, neurons firing haphazardly as they wobble and fall. But with practice, specific neural pathways strengthen, turning clumsy movements into fluid motion. This synaptic pruning and reinforcement mirrors the way galaxies mature. Young galaxies are chaotic, bursting with frenetic star formation, their gas clouds colliding in disorganized bursts. Over time, gravity smooths out the chaos. Galaxies settle into elegant spirals or serene ellipticals, their structures refined by mergers and the steady pull of dark matter. Both systems, brain and galaxy, start messy, then streamline, trading raw energy for efficiency. The mechanisms driving this complexity are strikingly similar. In the brain, Hebb's law states that neurons that fire together wire together. Repeated activation strengthens synapses, embedding skills and memories. In the cosmos, gravity plays the same unifying role. Galaxies that pass close enough begin a gravitational dance, their orbits intertwining until they merge, their stars and gas redistributed into a new, more complex whole. The Andromeda Galaxy, for instance, is on a collision course with the Milky Way. In about 4 billion years, these two spirals will fuse, their stars reshuffled into a single, larger galaxy, a cosmic version of neural networks consolidating knowledge. Yet there's a crucial difference in timing. While your brain can rewire itself in weeks, galaxies take billions of years to transform. Imagine if every time you learned a new fact, your neurons required a lifetime to form the right connections. That's the universe's timescale, patient, almost meditative, with change so gradual it's invisible to any single observer. But when we compare snapshots of the early universe to today's cosmos, the evolution is undeniable. Proto-galaxies, small and blobby, have given way to the majestic diversity of spirals, ellipticals, and irregulars we see now, each shaped by their unique history of collisions and growth spurts. This convergence of structure and function raises a tantalizing possibility. That complexity isn't an accident, but an inevitability. Whether it's neurons optimizing for information flow or galaxies settling into gravitational equilibrium, systems seem driven toward states where energy and organization balance. The brain's neural networks minimize wasted effort by pruning unused connections. The cosmic web does the same, with dark matter filaments funneling matter along the most efficient paths. It's as if nature has a favorite recipe for building complexity, one that works whether you're cooking up a thought or a galaxy. The implications ripple beyond astronomy and neuroscience. If the same principles govern growth at both extremes of scale, might they also apply to ecosystems, cities, or even artificial intelligence? Cities, for example, evolve like living organisms, their streets acting as arteries, their neighborhoods clustering like specialized brain regions. AI neural networks inspired by biology now exhibit similar learning patterns, strengthening some connections while discarding others. This isn't mere analogy. It's a reflection of how deeply these patterns might be woven into the fabric of reality. So the next time you memorize a fact or gaze at a galaxy, remember, you're witnessing the same universal story told in different languages. One unfolds in the spark of synapses, the other in the slow dance of stars. Yet both speak of growth, adaptation, and the beautiful inevitability of complexity emerging from simplicity. And in that shared narrative, we find a humbling truth that the universe and the mind might be more alike than we ever dreamed. Neuroscientists studying the brain's inner wiring made a fascinating discovery decades ago, that despite its billions of neurons, any two brain cells are just a handful of connections apart. This small world architecture allows lightning-fast communication, balancing localized clustering with long-range shortcuts. Now, astrophysicists are asking a startling question. Does the cosmic web follow the same blueprint? Could dark matter's filaments act like neural pathways, optimizing the universe's structure for efficient flow, not of electrical signals, but of matter and gravity? The idea isn't as far-fetched as it sounds. Both networks face similar challenges: how to move resources, whether information or galaxies, quickly without wasting energy. In the brain, densely connected hubs handle specialized tasks, while slender bridges link distant regions, creating a system that's both fault-tolerant and fast. Zoom out to the cosmic scale, and you'll see galaxy clusters as hubs, bound by filaments that serve as gravity's highways. Just as neurons minimize wiring costs to transmit signals efficiently, the cosmic web's filaments appear fine-tuned to shuttle gas and galaxies with minimal detours. Here's where the math gets compelling. When researchers analyzed the cosmic web's topology, they found it shares key metrics with neural networks like clustering coefficients and path lengths. Both systems exhibit small-worldness, meaning most nodes, whether neurons or galaxies, can reach others in just a few jumps. A galaxy in one filament might influence another millions of light-years away through a chain of gravitational interactions, much like a thought in your visual cortex can trigger a memory stored elsewhere in seconds. This isn't just analogy, it's a quantifiable pattern suggesting nature recycles its best designs. But why would such different systems converge on similar structures? One theory points to optimization. The brain evolved to process information swiftly while conserving energy, a biological imperative. The cosmic web, shaped by dark matter's gravity, naturally arranges itself into configurations where matter flows along the least resistant paths, avoiding chaotic tangles. Both networks arrive at efficient solutions because inefficiency gets penalized, whether by natural selection or thermodynamics. The implications ripple beyond academic curiosity. If the universe and the brain truly obey shared organizational principles, it could revolutionize how we simulate cosmic evolution. Astrophysicists already borrow algorithms from neuroscience to model dark matter's behavior, treating filaments like axons in a galactic-scale brain. These cross-disciplinary tools might one day crack mysteries like why some filaments glow with ultraviolet light while others remain dark, or how galaxies learn to align their spins with the web's structure over time. Yet the most profound takeaway is philosophical. If the same patterns govern neurons and galaxy clusters, it hints at universal laws of connectivity we're only beginning to decipher. Perhaps efficiency isn't just a human concern, it's woven into the fabric of reality, from the microscopic to the cosmic. And in that symmetry, we find a humbling reminder. The universe doesn't just contain complexity, it thrives on it, crafting order from chaos in ways that resonate across every scale of existence. Right now, we're seeing the cosmic web through a keyhole, catching glimpses of its grandeur, but missing the finer brushstrokes that could reveal its deepest secrets. Even our most powerful telescopes have limits, mapping only the brightest threads of this vast network while the dimmer filaments fade into the darkness. It's like trying to study a city's road system with only the main highways lit up. The side streets, the alleyways, the intricate shortcuts remain hidden, leaving the full picture frustratingly incomplete. But that's about to change. The James Webb Space Telescope, with its infrared eyes, peers through cosmic dust like never before, spotting the faint glow of gas clouds along dark matter filaments that older telescopes couldn't detect. Imagine upgrading from a blurry black and white photograph to a high-definition 3D model. Suddenly, the Webb's delicate strands come into focus, showing how galaxies migrate along these invisible currents. Meanwhile, the Vera C. Rubin Observatory will scan the entire southern sky every few nights, capturing time-lapse footage of the cosmic web in motion. This isn't just sharper imagery, it's a revolution in how we track the universe's growth, revealing how filaments twist, merge, and stretch over eons. These advancements aren't just about filling in missing details, they could expose hidden symmetries between cosmic and neural networks. Right now, the comparisons are striking but circumstantial, like finding two puzzle pieces that seem to fit without knowing if they're from the same box. With higher resolution data, scientists can analyze the cosmic web's branching angles, node distributions, and flow patterns with the same precision used to map brain connectivity. Do filaments transmit gravitational influences the way axons transmit electrical impulses? Do galaxy clusters fire in synchronized ways under certain conditions? The answers might lie in the subtle structures we've yet to resolve. There's even hope of spotting the universe's equivalent of synaptic pruning, the process where weaker neural connections fade to strengthen others. In the cosmos, this could manifest as filaments dissolving or rerouting when galaxies collide, redistributing matter to more stable pathways. Current telescopes catch the aftermath of these events. Next-generation instruments might witness them in real time, offering a dynamic view of how the cosmic web rewires itself. The stakes are higher than just cosmic cartography. If the parallels between these networks hold, it could reshape how we simulate everything from galaxy formation to artificial intelligence. Astrophysicists already borrow algorithms from neuroscience to model dark matter's behavior. What if those models become a two-way street, with cosmic data refining how we understand brain function? The universe, in a sense, might become the ultimate supercomputer, running a 13-billion-year-old experiment in network optimization that we're only now learning to decode. So while today's maps of the cosmic web are impressive, they're just the first draft of a much grander story. With every technological leap, we're not just building better telescopes, we're crafting a new lens to examine the hidden patterns that might unite the largest and smallest structures in existence. And in that quest, the line between astrophysics and neuroscience blurs, revealing a universe that thinks in networks, sculpted by forces we're only beginning to trace. Artificial universes are blooming inside supercomputers, not as science fiction, but as cutting-edge laboratories where scientists test the very fabric of reality. Picture this: a team of astrophysicists programs a virtual cosmos, tweaking the properties of dark matter like dials on a cosmic control panel. One simulation might give dark matter particles more mass, another might adjust how they interact, and yet another could erase them entirely, leaving gravity to play by different rules. Then, with the press of a button, they hit run, and the digital universe unfolds over billions of simulated years, compressing eons into weeks. The goal: to see which version grows a cosmic web that matches our actual universe, and which ones collapse into chaos or sprawl into formless voids. These aren't just video game recreations, they're precision experiments with staggeringly high stakes. Every flicker of light in a telescope, every distorted galaxy in a gravitational lens, every filament in the cosmic web carries clues about dark matter's true nature. But interpreting those clues requires a decoder ring, a way to test which theories align with reality. That's where simulations like Illustrious TNG or Eagle come in. By building thousands of virtual universes, each with slight variations, researchers can reverse engineer the rules that must govern our own. It's like hearing a symphony and trying to reconstruct the composer's sheet music, except the symphony is 13.8 billion years long, and the instruments are made of invisible particles. The results are humbling. Some dark matter models produce cosmic webs so sparse they'd leave galaxies isolated, like lone trees in a desert. Others generate filaments so dense they'd tangle the universe into a knot. But just a handful emerge with structures eerily similar to the real thing. Delicate threads of galaxies, vast voids, and clusters positioned exactly where our telescopes see them. These Goldilocks simulations don't just validate theories, they reveal hidden dynamics. For instance, they've shown that dark matter must be cold, slow-moving enough to clump into the seeds of galaxies, and that it likely interacts even less with ordinary matter than we thought. Otherwise, the cosmic web's intricate patterns wouldn't form. Here's where it gets even wilder. These simulations don't just passively predict, they've actively corrected our observations. When astronomers first mapped the cosmic web, they noticed some filaments appeared fainter than expected. Simulations suggested why. Gas in those regions was being heated by ancient quasars, their radiation lingering like cosmic ghosts. Without virtual universes to highlight this possibility, we might have dismissed the discrepancy as noise. Now, it's a key piece of the puzzle, showing how black holes and dark matter collaborate to shape the universe. But the real magic lies in the unexpected. Recently, a simulation called Sibelius, named after the composer, hinting at its artistic ambition, did something extraordinary. It recreated not just the cosmic web, but our local universe, complete with a virtual Milky Way and Andromeda, positioned just where they should be. When researchers compared it to real sky surveys, the match was uncanny, as if the simulation had peeked beyond the screen of reality. This isn't just a technical feat, it's a philosophical revelation. If we can simulate a patch of the cosmos so accurately, does that mean we're closing in on the universe's underlying code? Or are we simply tuning our models to reflect what we already see, like a painter copying a landscape without understanding the physics of light? The answer lies in the next generation of simulations, where artificial intelligence merges with astrophysics. Machine learning algorithms, trained on both real data and virtual universes, are now spotting patterns humans might miss, subtle correlations between dark matter halos and galaxy shapes, or hints that filaments might emit faint radiation we've yet to detect. These AI cosmic detectives could one day pinpoint which dark matter candidate, WIMP, actions, or something stranger, leaves the right fingerprints in the virtual clay. So while we can't yet reach out and touch dark matter, these digital universes are the next best thing. They're more than experiments, they're bridges between the seen and unseen, letting us test ideas no lab could contain. And with every simulation that mirrors reality, we're not just solving a cosmic mystery, we're learning to speak the universe's hidden language, one line of code at a time. Quantum gravity is the holy grail of modern physics, a theory that could finally unite Einstein's general relativity with the bizarre rules of quantum mechanics. These two frameworks govern the universe at opposite ends of the scale. relativity shapes galaxies and black holes, while quantum mechanics dictates the behavior of atoms and particles. But where they meet, where the immense gravity of a black hole crumples spacetime into a quantum-sized knot, our equations break down. Now, imagine if the cosmic web, with its dark matter filaments and galaxy-studded nodes, is quietly whispering the solution. What if the same quantum processes that flicker at the smallest scales also leave faint fingerprints in the largest structures of the cosmos? The idea isn't as far-fetched as it sounds. At its heart, quantum mechanics is about probabilities, particles existing in multiple states until observed, like a cosmic game of dice. Dark matter, meanwhile, defies classical physics, clumping in ways that suggest an underlying quantum choreography. Some theorists speculate that dark matter particles might be quantum objects on a galactic scale, their wave-like properties spreading across light years, subtly influencing how filaments form. Picture a single electron's probability cloud, fuzzy, spread out but magnified to the size of a galaxy cluster. The cosmic web's delicate branching could be the universe's way of collapsing these quantum possibilities into cosmic-scale certainties. Even more intriguing is the parallel to consciousness. Certain theories in neuroscience propose that quantum processes in microtubules, tiny structures inside brain cells, might play a role in how we think and perceive. If true, it would mean the brain harnesses quantum physics to generate consciousness, much like the cosmic web might encode quantum gravity in its structure. Both systems, brain and universe, would then be bridges between the quantum and classical worlds, translating probabilistic flickers into coherent, large-scale order. It's a dizzying thought. The same physics that allows you to ponder the cosmos might also govern the cosmos itself. Critics argue this is speculative, and they're right. No direct evidence yet links quantum gravity to dark matter. But the cosmic web offers tantalizing hints. Take the way filaments maintain their structure over billions of light years, resisting the universe's expansion. Classical gravity alone struggles to explain their resilience, but quantum entanglement, where particles remain mysteriously linked across vast distances, could provide a hidden reinforcement. If entangled dark matter particles exist, their connections might act like invisible threads, stitching the cosmic web together against the relentless pull of dark energy. The implications are staggering. If the cosmic web encodes quantum gravity, studying its filaments could be like reading a cosmic Rosetta Stone, deciphering the universe's deepest laws. Future telescopes, like the European Space Agency's Euclid mission, might detect subtle anomalies in the web's geometry, tiny kinks or vibrations that betray quantum effects. Even the web's eerie resemblance to neural networks could be more than coincidence. Both might emerge from similar mathematical principles, where information, whether gravitational or electrical, flows along optimal pathways. For now, this remains a frontier of what if. But history shows that the universe often hides its greatest secrets in plain sight. Once, we thought planets moved in perfect circles until Kepler saw ellipses in the data. Perhaps the cosmic web, with its filaments and voids, is another celestial clue, waiting for us to recognize the quantum handwriting scrawled across the sky. And if we do, it won't just solve a physics puzzle, it'll reveal that the universe, from its smallest particles to its largest structures, speaks a single, unified language. Dark matter's fingerprints aren't just etched across galaxies, they might be woven into the very story of life itself. Imagine the cosmic web as a colossal irrigation system, its dark matter filaments channeling rivers of gas and dust into fertile pockets where stars and planets could one day form. Without this invisible scaffolding, matter might have scattered randomly, leaving the universe a barren wasteland. Instead, dark matter's gravity sculpted dense regions where gas could cool, collapse, and ignite into stars that would later forge the carbon, oxygen, and nitrogen essential for life. It's a staggering thought. The same force that shaped galaxies may have also set the stage for biology's debut. Consider our own cosmic neighborhood. The Milky Way resides in a filament of the cosmic web, a relatively dense corridor where gas flows efficiently, feeding star formation for billions of years. This isn't just a lucky address, it's a direct consequence of dark matter's architecture. Regions too close to crowded galaxy clusters face constant bombardment from radiation, sterilizing any fledgling planets. Too far out in the voids, and stars are too sparse to seed heavy elements. But along the filaments, conditions are just right, sheltered yet resource-rich, like a valley between mountain ranges where water gathers and crops thrive. The timing matters too. Dark matter's early clumping jump-started galaxy formation, giving life a head start. If the universe had expanded just slightly faster, matter might never have clustered densely enough to ignite stars. Slower, and everything could have collapsed into black holes before life had a chance. This delicate balance, guided by dark matter's distribution, allowed galaxies like ours to emerge during the cosmic sweet spot, when the universe was mature enough to host heavy elements but young enough to avoid burning out. But the connection might go deeper. Some theories suggest dark matter could have directly influenced Earth's evolution. Hypothetical particles called WIMP, if they exist, might have collected in our planet's core, their annihilations generating heat that stabilized Earth's magnetic field, a shield protecting life from deadly solar radiation. Others propose that dark matter's gravitational nudges subtly altered asteroid orbits, steering water-rich comets toward early Earth. These ideas are speculative, but they highlight a profound possibility. That life didn't just arise despite the universe's dark side, but perhaps because of it. The most poetic idea of all, the cosmic web structure might make life statistically inevitable. If dark matter's filaments create countless Goldilocks zones across the universe, regions where matter concentrates just enough for chemistry to flourish, then life could be a natural outcome of the cosmos's architecture. Not a rare accident, but a predictable flowering of complexity, as inherent to the universe as spiral arms or supernova. This isn't just science, it's a paradigm shift. For centuries, we've seen life as separate from the cosmos, a fragile spark in the void. But if dark matter's hand guided life's origins, then biology and cosmology aren't just connected, they're chapters of the same story. A story where the universe, in shaping itself, unknowingly laid the groundwork for creatures who would one day look up and wonder how it all began. And that changes everything. The holographic principle turns everything we think we know about reality inside out, literally. Imagine the entire universe with its glittering galaxies and sprawling cosmic web as nothing more than a three-dimensional projection from information encoded on a distant, two-dimensional surface. It sounds like science fiction, but this radical theory, born from the study of black holes, suggests that dark matter might be the shadow of higher dimensional physics playing out on an unimaginably vast cosmic canvas. Just as a hologram stores a 3D image in a flat film, the universe's true structure, its mass, energy, even time, could be a kind of cosmic illusion, with dark matter acting as the hidden code that translates this 2D data into the rich, textured reality we perceive. Here's where it gets mind-bending. The cosmic web, with its intricate filaments and voids, might not just be shaped by dark matter. It could be a physical manifestation of that underlying holographic data. Think of it like a neural network in the brain, where memories aren't stored in single cells but distributed across countless connections. In the same way, the positions of galaxies, the curvature of spacetime, even the tug of gravity could all be emergent properties of information densely packed on some faraway boundary of the universe. Dark matter's ghostly presence, then, wouldn't just be a substance, it'd be a signal, a ripple in the hologram's code. This idea didn't come from nowhere. When physicists study black holes, they hit a paradox. The entropy, or information inside a black hole, seems to scale with its surface area, not its volume. That's bizarre, like saying a USB drive's storage depends on the size of its sticker, not its circuitry. The holographic principle emerged as a solution, proposing that the universe might work the same way. All the information needed to describe 3D space could be painted on a 2D surface at its edge, with dark matter as the brushstrokes that translate that data into the structures we see. If this is true, the cosmic web's resemblance to neural networks takes on eerie new meaning. Both could be examples of how information organizes itself when compressed into lower dimensions. Your brain's memories aren't localized, they're patterns woven across synapses, just as the universe's mass might be a pattern encoded on a distant horizon. The filaments of the cosmic web, then, wouldn't just be highways for galaxies, they'd be the universe's way of unpacking that compressed data into the 3D world we inhabit. Critics argue this is speculative, and they're right. No experiment has yet confirmed the holographic principle, and dark matter remains frustratingly invisible. But the math is tantalizing. Some models suggest that if the universe is holographic, dark matter's odd behavior, how it clumps but never collides, how it shapes galaxies but never emits light, could reflect the quirks of information propagating from a higher dimension. It's as if we're seeing the universe's pixels glitch, hints of a deeper resolution hidden just beyond our reach. The implications are staggering. If the cosmic web is a hologram, then dark matter isn't just a missing piece of the puzzle. It's the glue holding reality itself together. Every filament, every galaxy, even our own existence might be part of an unfathomably vast computation, a cosmic algorithm rendering spacetime from bits of quantum data. And if that's true, then the universe isn't just stranger than we imagine, it's stranger than we can imagine. A holographic masterpiece where every star, every thought, is a brushstroke on the surface of something infinitely deeper. Unlocking the secrets of dark matter isn't just about solving a physics puzzle, it's a philosophical earthquake, shaking the foundations of how we see ourselves in the cosmos. For centuries, humanity clung to the comforting notion that we were at the center of creation, the special protagonists in nature's grand story. Then Copernicus moved us from the center of the solar system. Hubble revealed our galaxy as one among billions, and now dark matter whispers an even more humbling truth. We're not just passengers on a small rock orbiting an average star. We're temporary patterns in an invisible web stretching beyond comprehension. This realization carries profound weight. If the cosmic web connects all matter like neurons in a universal brain, does that make us fleeting thoughts in a cosmic consciousness? Or merely dust clinging to the filaments of something far greater? The ethical dimensions of this discovery ripple outward like gravitational waves. Consider how we've historically exploited resources when viewing ourselves as separate from nature, mining, burning, consuming without regard for interconnected systems. Now imagine applying that same short-sightedness to a universe where dark matter binds everything. Future technologies might one day manipulate these invisible threads. Could we accidentally unravel the cosmic web's delicate balance while chasing energy or expansion? Already, proposals exist to harness dark matter particles as fuel or computation tools. Without understanding their role in maintaining universal structure, we risk becoming cosmic toddlers playing with matches in a galaxy-sized fireworks factory. Yet there's another, more hopeful perspective. Recognizing our place within this vast network could inspire a new planetary ethic, one that values connection over domination. Indigenous cosmologies have long described existence as an interconnected web, with humans as humble participants rather than masters. Modern physics might be catching up to this ancient wisdom. If dark matter's filaments literally link all galaxies, then polluting our planet or destroying ecosystems isn't just local damage, it's vandalism of the universe's grand architecture at one nodal point. This cosmic perspective could reframe environmentalism not as tree-hugging sentimentality, but as universal maintenance work. The psychological impact runs equally deep. Learning that 85% of reality's substance is invisible and alien forces us to confront how little we truly perceive. Our senses evolved to navigate African savannas, not quantum fields or galactic filaments. This sensory limitation creates an existential tension. We can mathematically describe dark matter's effects while remaining forever blind to its essence. Such humility might temper our technological arrogance, reminding us that for all our achievements, we're still decoding shadows on the cave wall of reality. Perhaps most unsettling is the timeline. Dark matter has shaped the cosmos for 13.8 billion years. Human civilization spans a cosmic eye blink. If we disappear tomorrow, the cosmic web will continue unfazed, its filaments threading through eternity without notice. This temporal insignificance could paralyze or liberate. Like surfers riding a wave they didn't create, we might learn to embrace our fleeting moment in the cosmic dance, finding meaning not in permanence but in participation. The ultimate ethical test may be how we share this knowledge. Dark matter research requires billion-dollar telescopes and supercomputers, luxuries many nations can't afford. Will cosmic understanding become another divide between technological haves and have-nots? Or could recognizing our shared place in this universal web inspire new forms of collaboration? The choice lies before us. Use these discoveries to erect new barriers, or let them remind us that beneath all human divisions, we're literally made of the same star stuff, woven into the same dark tapestry. This isn't just astrophysics, it's a mirror held up to our deepest assumptions about purpose, responsibility, and connection. As we stare into the dark matter abyss, we might find it staring back, not with answers, but with questions that redefine what it means to be human in an unseen universe. The next decade could rewrite our understanding of the universe as a new generation of experiments takes aim at dark matter's elusive secrets. Deep beneath the Black Hills of South Dakota, the LUX Zeppelin detector waits in a former gold mine, shielded from cosmic rays by a mile of rock. Its mission, to catch the faintest flicker of a dark matter particle colliding with liquid xenon, a signal so rare it might happen just a few times a year, like hearing a pin drop in a hurricane. Meanwhile, orbiting 1,000,000 miles from Earth, the Euclid Space Telescope scans the sky with razor-sharp precision, mapping the cosmic web structure across 10 billion light-years. Together, these projects represent humanity's most ambitious attempt to corner the universe's most elusive architect. What makes this moment so electrifying isn't just the technology, it's the stakes. For 80 years, dark matter has been the ultimate cosmic ghost, its existence inferred solely by the gravitational ripples it leaves behind. But indirect evidence can only take us so far. Imagine trying to study elephants solely by their footprints. You might deduce their size and weight, but you'd miss everything about their biology, their behavior, their very essence. LUX Zeppelin and Euclid aim to shift the game from footprints to photographs, offering our first direct glimpse of the particles that bind the cosmos. LUX Zeppelin approach is brute force simplicity: wait, listen, and hope for a whisper. Filled with 10 metric tons of ultra-pure liquid xenon, Its core is one of the quietest places on Earth, or rather, under it. When a dark matter particle, perhaps a WIMP, bumps into a xenon atom, it should produce a flash of light and a burst of electrons, captured by sensors so sensitive they can count single photons. The challenge: everything else in the universe also wants to crash this party. Cosmic rays, radioactive decay in the detector's own materials, even neutrinos from the sun create false alarms. Filtering out this noise requires engineering wizardry. Copper purified in medieval castles where old lead roofs block modern radiation, xenon distilled to remove trace krypton, and layers of shielding that turn the detector into a fortress against interference. Euclid takes the opposite strategy. Instead of hunting individual particles, it surveys the cosmic web's grand architecture. By measuring how light from distant galaxies bends around dark matter filaments, a phenomenon called weak gravitational lensing, it will reconstruct the invisible scaffolding in 3D across a third of the sky. Previous telescopes saw these distortions as blurry smudges. Euclid's 16 high-resolution megapixel camera captures them with HD clarity. The result: a time-lapse of dark matter's evolution, showing how filaments grew from faint whispers in the early universe to the backbone of today's galaxies. But the real magic happens when these projects collaborate. If LUX Zeppelin detects a particle with specific properties, Euclid can check whether those traits align with the cosmic web structure. Conversely, if Euclid finds unexpected kinks in filaments, LUX Zeppelin can adjust its search parameters. It's like solving a puzzle where one team works from the edges while the other fills in the center, and the picture emerging could redefine physics. The implications ripple far beyond astrophysics. If dark matter particles are found, their properties might hint at undiscovered forces or extra dimensions. If Euclid reveals filaments behaving oddly, it could suggest dark matter isn't a single substance but a family of particles, each playing a different role in cosmic evolution. There's even a chance these experiments will find nothing, a result that, while frustrating, would force a radical rethink of gravity itself. This isn't just science, it's a testament to human curiosity. From gold mines to deep space, we're weaving a net to catch the uncatchable, driven by the audacious belief that the universe's deepest secrets are within our grasp. And whether the answers come in flashes of light or maps of the void, one thing's certain: the cosmic web is about to lose some of its mystery, and we're here to witness it unravel. The cosmic web and the human brain, two networks separated by scale, yet united by design. One sculpted by dark matter's invisible hand, the other forged by billions of firing neurons. But their uncanny resemblance isn't just a curiosity, it's a cosmic clue, whispering that the universe might operate by a shared set of hidden rules. Whether it's galaxies clustering along dark matter filaments or neurons wiring together to form thoughts, both systems thrive on connectivity, balancing order and chaos to create something greater than the sum of their parts. This isn't mere coincidence, it's a testament to how nature, when faced with similar challenges, often converges on the same elegant solutions. Consider the math behind these structures. The cosmic web's filaments and your brain's neural pathways both follow what scientists call scale-free networks, patterns where a few highly connected hubs link countless smaller nodes. In the brain, these hubs are critical regions like the hippocampus, orchestrating memory and learning. In the cosmos, they're galaxy clusters, gravitational anchors that bind entire superclusters together. Both systems avoid unnecessary redundancy, optimizing for efficiency. Your brain doesn't waste energy wiring every neuron directly to every other. Instead, it builds strategic shortcuts. Just as the universe doesn't tangle galaxies randomly, it threads them along filaments, the cosmic equivalent of neural highways. What's even more striking is how these networks evolve. A child's brain prunes unused connections as they learn, strengthening only the pathways that prove useful. The cosmic web undergoes a similar refinement. Early in the universe's history, galaxies formed in chaotic bursts, colliding and merging without clear order. Over billions of years, dark matter's gravity smoothed out the chaos, funneling galaxies into the web's stable filaments. Both systems start messy, then self-organize, as if guided by an invisible algorithm favoring resilience and adaptability. Could this symmetry point to something deeper? Some theorists suggest that the universe itself might function like a vast, self-aware system, with dark matter's web acting as its nervous system. It's a provocative idea, one that blurs the line between physics and philosophy. After all, if the same patterns govern galaxies and gray matter, could consciousness itself be a natural outcome of how information organizes at scale? Or is this just a case of humans seeing patterns where none exist, projecting our own biology onto the cosmos? The answer might lie in the next frontier of discovery. As we build more powerful telescopes and simulations, we're not just mapping dark matter, we're decoding the universe's operating manual. Every filament traced, every neural analogy tested, brings us closer to understanding whether these parallels are profound truths or beautiful accidents. Either way, one thing's certain: the universe is far stranger, far more interconnected than we ever dreamed. So what do you think? Is the cosmic web just gravity's masterpiece, or could it be something even grander, a network humming with a logic we're only beginning to grasp? Drop your thoughts in the comments below, and if you've enjoyed this journey through the universe's hidden architecture, don't forget to subscribe. The cosmos is full of mysteries waiting to be unraveled, and we're just getting started.